Welcome to Study Loop.
Hi, in the given problem, here this is a circular loop of a conducting wire which is lying in the XY plane, and there is a magnetic field in the direction of positive z-axis. The given parameters are for the radius of this loop R0. This is equal to 0.0420 meter, and this magnetic field, which is varying with the time in the direction of positive z-axis, that is given as B bar is equal to B naught 1 minus 3 T by T naught to the whole square plus 2 times of T by T naught to the cube Tesla K cap, where K is the unit vector along z-axis. The values of these constants means T naught is a constant whose value is 0.0100 second, and B naught is having a value of 0.0800 Tesla. The resistance of the circuit which is attached with this coil is given as R is equal to 12.0 ohm. Now, in the first part of the problem, we have to find an expression for the magnetic flux linked with the coil. And we know this is given as the dot product of magnetic field with the area vector. As coil is lying in XY plane, so we can say this area vector will be given by pi times of R naught square K cap, means this area vector is also lying in positive z-axis, in the direction of positive z-axis. So the expression for this flux will become B A cos 0 degree, as the magnetic field and area both are lying along positive z-axis, so the angle between them is 0 degree. So it is simply equal to the product of magnetic field expression with the area. So it comes out to be B naught 1 minus 3 times of T by T naught to the whole square plus 2 times of T by T naught to the whole cube multiplied by area, which is pi R naught square. So finally, the expression for magnetic flux as a function of time comes out to be B naught pi R naught square multiplied by 1 minus 3 times of T by T naught square plus 2 times of T by T naught cube Weber, which is the SI unit of magnetic flux. Now, in the second part of the problem, we have to find the value of EMF induced. So, using Faraday's law of electromagnetic induction, the expression for EMF induced in the coil as a result of rate of change of magnetic flux is given by the time rate of change of magnetic flux, the negative of. The negative sign is used as per Lenz's law. So this is d phi b by dt, means time derivative of the function of magnetic flux. It will be, so we can say it will become minus b naught pi R naught square as a constant will come out. Now we have to differentiate the three terms in this bracket. first term is 1, which is a constant, so its derivative with respect to time will come out to be 0, and then the derivative of 3 times of t naught will be constant, and then it is derivative of 2 times of t cube. This is 3 times of t square, and this is 2 times of t cube. T naught will be constant. So these derivatives will become 0 minus 3 times of t naught square, then the derivative of t square is 2 times of t, plus 2 divided by t naught cube, and then the derivative of t cube, which will become 3 times of t square. So finally it will come out to be minus b naught pi r naught square 6 by t naught cube multiplied by t square minus 6 by t naught square multiplied by t. Now we have to find this EMF induced at a time of 5 multiplied by 10 raised to the power minus 3 second. At this much second we have to find the EMF induced. So putting all the values of the EMF and constants B naught, T naught and time, all the things are known. So when we put all these values, the EMF, induced EMF comes out to be, this is minus 0.08 for magnetic field multiplied by 3.14, then for radius this is 0.0420 to the whole square, then in the bracket this is 6 by 0.01 to the cube multiplied by 5 into 10 raised to the power minus 3 square minus 6 by 0.01 square multiplied by 5 into 10 raised to the power minus 3. So we get, this is minus 4.43 multiplied by 10 raised to the power minus 4. In the bracket it is 150 minus 300, which finally comes out to be 6.65 multiplied by 10 raised to the power minus 2 volt, or we can say this is 0.0665 volt. So this is the answer for the second part of the problem, for the EMF induced. Now, in the third part of the problem, we have been given the net current induced in the coil, and that has been given as 3 milliampere. So it will become 3 multiplied by 10 raised to the power minus 3 ampere. So using the expression for current, using Ohm's law, this is given as EMF divided by the resistance of the circuit plus internal resistance of the coil, let it be small r. So finally this R plus R will be given by EMF induced divided by current. Here this EMF induced is 0.0665 divided by 3 into 10 raised to the power minus 3, which finally comes out to be approximately 22.2. So this internal resistance of the coil will come out to be 22.2 minus 12, or this is 10.2 ohm. In the second part of the problem, we have to find the direction also of the induced current, because we have to find the polarity also. So as when we look at this term, if we look only for the flux, this is the expression, this is the bracket for the flux, and if we put the values of constant, means T naught, and time 5 into 10 raised to the power minus 3 second, definitely this bracket comes out to be negative. means the reason behind the EMF induced will be this flux, which is outward as it is along the z-axis. So we can say this magnetic flux, this magnetic field will be coming out of this coil. So the reason behind the EMF induced is outward decreasing magnetic flux. So as per Lenz's law, its opposition will be outward increasing magnetic flux, means this will be the induced magnetic flux, outward increasing. And as you know, magnetic field comes out of the north pole. So this phase of the coil should start behaving like the north pole, or we can say the direction of current induced should be counterclockwise. This was the answer of the second part as well. Now, this is the third part. Now, in the fourth part of the problem, the time now has been given as 1.21 multiplied by 10 to the power minus 2 seconds. And again, we have to find the EMF induced. So, again, we will put the values here in this expression for the EMF, this one. So, putting the values in equation number 1 again, we will get the EMF induced to be the constants outside the bracket will get the same values because there is no time included in it. So here it is minus 4.43 into 10 raised to the power minus 4 bracket. Now the derivatives of the three terms, 0 for 1 and minus this is 0.01 to the whole square multiplied by 1.21 into 10 raised to the power minus 2 plus 6, 0.01 to the cube, 1.21 multiplied by 10 raised to the power minus 2 to the whole square. So it takes a form minus 4.43 into 10 raised to the power minus 4. This is 878.46 for this third term, and minus this is 726. So finally this EMF induced comes out to be minus 0.068 volt. And for the direction, if we look here at this flux, here this flux will be now positive, means the reason behind this EMF induced is outward increasing magnetic flux. So its opposition will be inward increasing magnetic flux as per Lenz's law. It is inward increasing. And as we know, magnetic field enters into the south pole. So this phase of the coil should start behaving like south pole. So the direction of current induced is clockwise. Now, in the last part of the problem, we have to find the time when this current changes its direction from counterclockwise to clockwise, and definitely it will happen when the EMF induced once will become 0. So putting this value of EMF induced to be 0 in this expression number 1, we will get this 0 minus 6 by t naught square into t plus 6 by t naught cube into t square to be equal to 0. Or we will get here, this is 6 by 0.01 to the square t is equal to 6 by 0.01 cube t square. This t will be cancelled. So this is 60,000 is equal to 6 million t. So finally this time comes out to be 60,000 divided by 6 million. So this comes out to be 0.01 second. So at a time of 0.01 second, the current will change its direction from counterclockwise to clockwise. Thank you.